Welcome! In this multivariate calculus tutorial, we're going to do double integrals and change of order of integration, and then we'll look at some more complicated examples after that. So if you're interested in that, then stay tuned. All right, so in our first question, we're asked to calculate the double integral of 6x squared y minus 2x dy dx. It's a definite integral. So since the y is on the inside, this is y down here. So 0 to 2, and the x is going from 1 to 4. Let's get a visual on this. So I'll pull up a Mathematica plot that I've done. Okay, so here you see the surface plotted in some region, and then there's a box. All right, and so the box is these bounds right here. So the y is going from 0 to 2, okay, and so that's this side up to this side. The x is going from 1 to 4. So from 1 to 4. And so what we're doing in this calculation is we're calculating the area under this surface down to the plane z equals 0. So that's the bottom here. So for example, how much volume of, say, water could you fill up from z equals 0 all the way up to the top of this surface within this little box? Okay, so that is what this calculation is. So let's begin to do the calculation. So we need to treat the other letter other than y here as a constant when we integrate this. And so first we'll leave the 1 and the 4 and the integral sign in place, and we'll just do the inside. Okay, so we're going to evaluate this between 0 and 2. So we'll put in a square bracket inside. And because this can get a little bit confusing, I like to put in y equals 0. This goes with y to y equals 2, so we don't accidentally sub into the x value that we're going to get, these x values here. Okay, so now let's integrate this function. We're integrating with respect to y, so we add 1 to the exponent of y there, divide by that new exponent, which is 2. So 6 over 2 is 3x squared y squared. And if you just differentiate this partially with respect to y, you will get 6x squared y. Okay, and so we'll do the same thing with minus 2x. So here we are treating minus 2x as a constant. We have minus 2x times y. Okay, so next we sub in y is 2 into this function. We subtract this function of y equals 0. We leave our integral sign in place here because we're not integrating that just yet. Okay, so let's sub in y is 2. So we have 3x squared. 2 squared is 4 minus 2x times 2. So that's minus 4x, and then we subtract this in brackets because we're subtracting the whole thing. So 3x squared times 0 squared minus 2x times 0. So obviously this one in brackets is just 0 because we have 0 here and here. So let's simplify this now. So we have 12x squared minus 4x. And so now you can see we have an integral of just one variable. Okay, so we need to integrate 12x squared with respect to x. We add 1 to the exponent, divide by the new exponent. So the new exponent is 3. 12 over 3 is 4. So 4x to the power of 3. If we differentiate this, we would get 12x squared. Now let's integrate minus 4x. We add 1 to the exponent of 1, and we get 2. We divide by the new exponent, so we have 4 over 2 is 2, so 2x squared. And this is x goes from 1 to 4. Okay, so now we sub in the 4, we sub in the 1, and we subtract. So 4 times 4 to the power of 3 minus 2 times 4 squared, and then we subtract in brackets 4 times 1 cubed minus 2 times 1 squared. Okay, so let's simplify this. So this is 4 to the power of 4, so 4 squared is 16, 16 squared is 256, and then we have 2 times 16, so subtract 32, and then over here we are subtracting 4 minus 2 is 2, so 256 minus 34 should give us 222, down to the xy plane, which is the plane z equals 0. That volume is 222 units. Okay, so in question 2 here, we've got a double integral of x plus y all squared between 0 and 1 and 0 and 1. So again, we are calculating the area under the surface within this box beneath the surface down to the xy plane, the plane z equals 0. So it's how much volume can fit into this region here under the surface. Okay, and so let's calculate this now. So we still write our outside of this. Now let's integrate the inside. Probably the easiest way to do this would be to expand the inside of this. So x squared plus 2xy plus y squared integrated with respect to y. And so we have the integral from 0 to 1. Integrating this function with respect to y, we have x squared y plus x y squared plus a third y cubed between 0 and 1. And that's y equals 0 to y equals 1. And then we integrate the result with respect to x. Okay, so let's substitute in y equals 1. We have x squared times 1 plus x times 1 squared plus 1/3 times 1 cubed. And we subtract when we put in 0 here. So we have x squared times 0 plus x times 0 squared plus 1/3 0 cubed. Now, of course, this is just 0 because we have 0 everywhere there. And so we have the integral from 0 to 1 of x squared plus x plus 1/3 with respect to x. So integrating this function, we have 1/3 x cubed plus a half x squared plus 1/3 x from 0 to 1. So let's sub in the 1. We have 1/3 times 1 cubed plus 1/2 times 1 squared plus 1/3 times 1. And then minus, in brackets, 1/3 times 0 cubed, half times 0 squared, and 1/3 times 0. So simplifying this, all of this here is 0. So what we have then is 1/3 plus 1/2 plus 1/3, which is 2/3 plus 1/2. Now writing this over 6, we have 4 over 6 plus 3 over 6, and we get 7 over 6. The volume under the surface is 7 over 6. Question 3. So again, we have a double definite integral, x plus e to the power of minus y, first integrated with respect to x as x goes from 1 to 2, and then integrated with respect to y as y goes from 0 to 1. And so here we have a picture of this surface and some bounds. So the bounds go from 1 to 2 in x and from 0 to 1 in y. So there's the 1 to 2 in x and then the 0 to 1 in y. And we're calculating the area under this surface down to the xy plane, or z equals 0. So let's begin this calculation. So we first integrate this with respect to x. We have a half x squared plus x e to the minus y from 1 to 2, and that's x equals 1 to x equals 2, and then we integrate the result with respect to y. Okay, so let's substitute in x equals 2. So we have a half times 2 squared plus 2 e to the minus y. Subtract, now we sub in 1, half times 1 squared plus 1 times e to the minus y. Okay, and so let's simplify this. So 2 squared is 4, 4 over 2 is 2, subtract a half, and subtract e to the minus y. Okay, so simplifying what we have inside before we integrate, 2 minus a half is 4 over 2 minus 1 over 2, which is 3 over 2. 2 minus 1 is 1. Okay, and so now integrating this with respect to y, 3 over 2y, then minus e to the minus y, y equals 0 to 1. And so now subbing in y as 1, so 3 over 2 times 1, minus e to the minus 1, subtract 3 over 2 times 0, minus e to the 0. So we have 3 over 2 minus 1 over e plus 1. And so this is 5 over 2 minus 1 over e, or minus e to the minus 1 if you like. Okay, so this is the volume under that surface between x equals 1 and x equals 2, and between y equals 0 and y equals 1, and above the z equals 0 plane. Question 4. Okay, so here we can see the surface that we're calculating the volume under within this rectangular region here down to the plane z equals 0. We're calculating the volume under the surface within that region. Okay, so let's begin the calculation. So integrating sine x with respect to y gives y sine x. Integrating sine y with respect to y gives minus cos of y. And so y equals 0 to y equals pi on 2. And then we integrate the result with respect to x. Okay, so let's sub now y equals pi on 2 in for the y values. And now let's sub in y equals 0. Okay, so simplifying what we have here, So we have pi on 2 sine x. Cos of pi on 2 is 0. So it's minus 0. Then we have another minus 0 there. And minus cos of 0. That'll be plus 1. Okay, now integrating this with respect to x, we have pi on 2 times the integral of sine of x with respect to x, which is minus cos of x. And then the integral of 1 is x. We sub in 0 and pi on 6. Okay, and so we've subbed in both of those values. So here's the expressions. And now we need to simplify this. So cos of pi on 6. Now pi on 6 is 30 degrees. Let's draw a little triangle here to remind us how this works. Right triangle with sides 1, 3, and 2. The smaller of the two angles is pi on 6. The larger one is pi on 3. And so cos of pi on 6 is root 3 over 2, okay, plus pi on 2. All right, so these all have a common pi on 2. We can factor that out. And so then what remains is 1 plus 1/3 minus root 3 on 2. And so simplifying what's in the brackets there, we want to have a denominator for these equal to 6. Okay, so there it is over 6. 6 plus 2 is 8. 2 times 6 is 12. So we have pi on 12 outside of 8 minus 3 root 3. Question 5. So question 5 says, find the volume of the solid that lies under the plane 4x plus 6y minus 2z plus 15 equals 0 and above the rectangle R, which is the collection of all points such that x is greater or equal to minus 1, less than or equal to 2, and y is greater or equal to minus 1, but less than or equal to 1. So first thing, let's draw a little rectangle representing R. Okay, so there's the axes, and now I'll just draw lines for x equals minus 1, and then x equals 2. Okay, then y equals minus 1 to y equals 1. All right, and then let's shade this. And so this here is our region R. So we're calculating the volume of the plane within this region, above that and down to the xy plane. And so I've got a plot here to show you. Here's the region. The region looks like a square, but I just haven't set the aspect ratio to display that it's not a square. And then the plane that we're calculating the volume under is shown here above the xy plane. So we're calculating the volume under this. Now you can see that there are no intersections with the xy plane, so this volume will not subtract from itself. Okay, so let's set up our integral to calculate. And so we've got the V, the volume, is a double integral over the region R of 1/2 4x plus 6y plus 15 dA. Okay, so why have we written down this? Well, what I've done here is just taken the equation for this plane, taken the minus 2z over to the other side of the equation so that we have 2z equals 4x plus 6y plus 15. Then we divide that by 2, so we have z as a function of x and y. So that's 1/2 of 4x plus 6y plus 15. Okay, and so now we can expand that 1/2 in. That might make it easier to integrate. So what about the bounds of integration? So we want to write this in terms of dx and dy, or dy dx. So let's put dy first and then dx. So the y's in here are going from -1 to 1, and the x's are going from -1 to 2. And so inside we have 2x plus 3y plus 15 over 2. Okay, so now we can just integrate this and calculate the volume shown in the diagram there. So integrating 2x with respect to y gives 2xy. Integrating 3y with respect to y gives 3 over 2 y squared, and then integrating 15 over 2 with respect to y gives 15 over 2 y. This is from y equals -1 to y equals 1. Okay, subbing in 1, 2x plus 3 over 2 plus 15 over 2, and then minus. Now we'll sub in -1, so minus 2x plus 3 over 2 minus 15 over 2. Okay, now simplifying this difference, 2x plus 2x is 4x, 3 over 2 minus 3 over 2 is 0, 15 over 2 plus 15 over 2 is 15, and so now we need to integrate 4x plus 15. So we have 2x squared plus 15x from minus 1 to 2. And so subbing in the 2 now, we have 2 times 2 squared. So 2 times 4 is 8. 15 times 2 is 30. And then subtract. Be careful here because there's a negative there. It can get confusing. So subtracting 2 times minus 1 squared is 2. 15 times minus 1 is minus 15. And so inside the bracket, we have minus 13. Minus 1 times minus 13 is plus 13. 13 plus 38 is 51. So we have a volume under the surface here equal to 51. Okay, so in question 6, we're asked to find the volume of the solid that lies under the hyperbolic paraboloid z equals 3y squared minus x squared plus 2 and above the rectangle minus 1 to 1 Cartesian product or cross 1 to 2. So we can write this in another way. This is the set of all points x comma y such that x is greater or equal to minus 1 but less than or equal to 1, and y is greater or equal to 1 but less than or equal to 2. Okay, and so we have this displayed here. So you can see the surface inside the box, and the box itself is the rectangle from minus 1 to 1 and from y going from 1 to 2. Okay, so now let's set up our volume calculation. So this is a double integral over the region R of z, which is 3y squared minus x squared plus 2 dA. Okay, so now let's convert this into an integral that we can actually calculate. So we'll put dy first and then dx, but you could put it either way because we have a rectangle here, 3y squared minus x squared plus 2. Now the y goes from 1 to 2 and the x goes from minus 1 to 1. Okay, so integrating this function with respect to y, we have y cubed minus x squared y plus 2y. Y goes from 1 to 2, and then integrate this result with respect to x. Okay, so subbing in 2 cubed is 8 minus 2x squared. 2 times 2 is 4. Then we subtract 1 cubed is 1 minus x squared times 1 plus 2 times 1 is 2 dx. Okay, so simplifying this, 8 plus 4 is 12, minus 3 is 9, minus 2x squared plus x squared is minus x squared. And now we integrate this with respect to x. So we have 9x minus a third x cubed. So now let's sub in the 1. So 9 times 1 minus 1/3 times 1, subtract minus 9. Now minus 1 cubed is minus 1, so this is plus 1/3. Simplifying, we have 9 minus a third plus 9 minus 1/3. So 9 plus 9 is 18. So this is 18 minus 2/3. Putting this over 3, 18 times 3 is 54. So 54 minus 2 over 3 is 52 over 3. We have a volume under that surface of 52 over 3. Okay, question 7. Calculate the volume of the solid enclosed by the surface z equals x squared plus x y squared, and the planes z equals 0, x equals 0, x equals 5, y equals plus or minus 2. Okay, so that's what we see here. We're calculating the volume under this surface here within this box. So our box goes from 0 to 5 in the x's, and the box goes from minus 2 to 2 in the y's. And then it looks like the highest corner of this is around 45 or so, but I'm not sure. Okay, so we're calculating the volume under this. All right, so we need to set up an integral. So that volume is double integral over the region R of x squared plus x y squared dA. Now the region R is the set of all x, y, such that x is greater or equal to 0 but less than or equal to 5, and y is greater or equal to minus 2, less than or equal to 2. And so that is a rectangular region. So it doesn't matter if we put the dy first or the dx first. We just need to match up the bounds correspondingly. Okay, so let's go ahead and put the y first and then the x. So the y values here go from minus 2 to 2. The x values go from 0 to 5. And now we can integrate with respect to y. So the integral of x squared with respect to y is x squared y. Integrating x y squared with respect to y gives 1/3 x y cubed minus 2 to 2 and then dx. Okay, so subbing these numbers in, this is y equals minus 2 to y equals 2. So we sub in y is 2, so that gives us 2x squared. Then we have 2 cubed is 8, so 8 over 3x. And then we are subtracting. Now we're subbing in minus 2, so minus 2x squared. Minus 2 cubed is minus 8, minus 8 over 3x. Okay, now taking the difference, we have 2x squared plus 2x squared is 4x squared. 8/3 x plus 8/3 x is 16/3 x. All right, so integrating this, we have 4/3 x cubed plus 16 over 3 times 1/2 x squared, but 16 over 2 is 8, so that's plus 8 over 3x squared, 0 to 5. Okay, now we sub in the 5. We have 4 times 5 cubed over 3 plus 8/3 times 5 squared. And then when we sub in 0 here, we just have 0, so I'll put minus 0. Okay, so now we need to simplify this. 5 cubed is 25 times 5, which is 125. 125 times 4 is 500. So 500 over 3, but this is also over 3. So 25 times 8 is 50 times 4, which is 200. And so 500 plus 200 is 700. So we have a volume of 700 over 3. Okay, question 8. So in question 8, we're just given the double integral. We don't need to think about how to set that up. So integrating first with respect to x, we have a half x squared y squared. Okay, and so then we need to sub in the 1 and the 0, the x that we're subbing in. So we have 1/2 y squared minus 0 dy. Okay, and now integrating 1/2 y squared, we have the integral of y squared with respect to y is 1/3 y cubed. So we have 1/6 y cubed, 2 to 4. Okay, and so this is 1/6 of 4 cubed minus 1/6 of 2 cubed. So 4 cubed is 16 times 4, which is 64. So 64 over 6 minus 8 is 2 cubed over 6. And so this is 56 over 6, but we can reduce this and call this 28 over 3. Question 9. So we have a double integral as y goes from 0 to 2 and x goes from 0 to 1 of y over xy plus 1 to the power of 2. So this one looks like it will work out by substitution. So let's let u be equal to xy plus 1. Okay, so if it's going to work out by substitution, then we'll have a nice relationship with the partial derivative of u with respect to x and what we have there in the numerator. So taking the partial derivative of u with respect to x, we just have y. Now notice that is exactly the numerator, but the important thing that will make this work out is if it's a constant times the numerator. So yes, it is. And so here we want to replace the dx. Now just do some algebra on this, pretending as though this is a fraction when it's not, but it tells us how to make that substitution. And so we can see that we replace dx with du over y in here. And so this is our substitution. Okay, and so this tells us how to calculate the integral. So we have the integral of y over u squared du on y. So now we can cancel the y, and we just have the integral of u to the minus 2 du, which is minus u to the minus 1. Adding 1 to that exponent and dividing by the new exponent, plus c. Okay, now this is a definite integral. So let's see what we have here is minus 1 over xy plus 1. And then plus c for this, but this is a definite integral, so this integral here is the integral from 0 to 2 of minus 1 over xy plus 1. Then we have bounds of integration 0 and 1. Okay, and so now we sub in, now this is x that we're subbing in here, so we sub in x is 1. We subtract, now we sub in x is 0, so we just have minus 1 over 1. And so simplifying this, let's write this minus brackets y plus 1 to the minus 1, and then I'm just going to leave this as plus 1 because I think it makes this easy enough to integrate. So integrating this now, we can pull the minus out. The derivative of y plus 1 with respect to y is just 1. So this integral will be the natural log of y plus 1, which I'll write ln for. And then the integral of y with respect to y is just y. Okay, so we have this. Now let's get some more paper. So we have minus natural log of 2 plus 1 is 3 plus 2. And then we subtract minus natural log of 0 plus 1 is 1 plus 0. So the natural log of 1 is 0. E to the power of 0 is 1. So all of this is just 0. So we have 2 minus the natural log of 3. All right. So now, if you don't believe me, let's do the same thing in Mathematica here. We can do this with a double integral. So our question here had y over xy plus 1. And then we're integrating x goes from 0 to 1 and y goes from 0 to 2. Oh, I see. I forgot the square, didn't I? Okay. So I'll put in the square. And there we have 2 minus natural log of 3. Question 10. So in question 10, we have a double integral from 1 to 2 as y goes from 1 to 2. X goes from 0 to y squared. The integral itself is fairly simple. The region in this one is a little bit more complicated. It's not a rectangular region. So if you want to swap the order of integration here, you can't use Fubini's theorem because it doesn't apply. So you have to take a little bit more care to do that. I want to do this one in two ways. And so you can see here up in the PDF, the region itself is shaded. And so we're calculating the area under a surface within this region. So the curve that you see here is the curve, not y equals x squared, but x equals y squared. Okay, so let's go to Mathematica now and give you a little bit more details on how to plot this region. So I'm going to write region plot. I think I can do a 3D version of this. Okay, good. Region plot 3D. Let's enter the function in. Okay, and so z will be less than this. I can see that I need to clear all z here. Okay, I'll put brackets around this and then a double and symbol for and. I'm putting in logical conditions. Okay, so the next one is that, okay, so here x goes from 0 to y squared, and then let's put in another and. Okay, and so now let's put in our bounds. So x, I'll put in larger than necessary here, and then we'll adjust it after we have a look at it. Okay, so this is what it shows us. This does not quite look like the region we were looking at. So there's an option in region plot where we can increase the number of points. Okay, so yeah. Okay, so here I've changed the surface to 1 just so I can make sure that this looks like this first, and I can see that the x value, I need to take that to 4. Okay, so this region to me now looks like this region. So the next thing to do is replace the 1 with x y squared, and maybe we need to even increase the z values. Let's have a look. Yeah, I think so. Not quite there yet. Let's go to something like 20. Okay, yes, I can see a sharp point there. So what is the height of this? It's probably somewhere around 15. Well, it's 16, isn't it? Because it's 4 times 4. Let's just take that to 16. All right, and so here is the region that we are calculating the volume of. So you can see it's got a very unusual shape. Okay, so now let's get back to calculating this. Put this up here for now. Okay, so first we'll do this the easy way. Now, straight away, you probably want to put in here that this is x on the bounds here. So x equals 0 to x equals y squared. So now let's integrate this partially with respect to x. So we have a half x squared times y squared. X goes from 0 to y squared. Okay, so we're going to sub in replacing x with y squared there. So half y squared squared, and then y squared, and we subtract. Now we're subbing in 0, so we're just subtracting 0. We're going to integrate this with respect to y. Okay, so simplifying this, we have a half y to the 4th times y squared is y to the power of 6. And so we get 6 plus 1 is 7, so we're dividing this by 7. So 1 over 2 times 7, 14. Y to the power of 7, 1 to 2. So now we sub in 2, we sub in 1, we subtract. And so we have 2 to the power of 7 minus 1 all over 14. Now 2 to the power of 7 I'm pretty sure is 128, but I'll check. There we go. Yes, 128. So 127 over 14 is the volume of this strange looking object. Okay, so now we're going to change the order of integration and hope to get the same number. Let's go ahead and do that. But to do that, we need to be careful about the region itself. So that region there that you have on the PDF in blue, I'm going to describe that region in two ways. So that's the set of all points x, y such that x is greater or equal to 0 but less than or equal to y squared, because at the boundary that black curve is the curve x equals y squared. This is talking about the x's, and then the y goes from 1 to 2. So if we change the order of integration, then we need to describe this differently, and that's what that pink dotted line is about there. So in the alternative representation, we can describe this as the set of all points x, y, such that x is between 0 and 1. Okay, so from 0 up to the dotted line, and y is between 1 and 2. Now this just describes this rectangle here on the left, and so we need a union of another set. That's the set of all points x, y such that x is between 1 and 4. Okay, so look at this. The x goes from here up to the point where the line y equals 2 intersects with this curve x equals y squared, and that happens at 4. And then the y is greater or equal to the square root of x. Now notice this right here on the boundary is the curve x equals y squared. And so y goes from there to 2. Okay, so we've got a union of two sets. And so this means that when we change the order of integration, we're going to express our integral as a sum of two definite integrals. So we have the integral from 1 to 2 from 0 to y squared, xy squared, dx, dy, changing that order of integration, meaning we're putting the dy on the inside and the dx on the outside. So we still have the same function here, but we're changing the order. So let's just put a sum of two things. We know we've got a union here of two sets, and then let's work out what we're going to put on the bounds next. So all we've done so far is put the dy on the inside and the dx on the outside. Okay, so next, if this represents the volume within that rectangle, then we're looking at this part of it. So we have y going from 1 to 2, we have x going from 0 to 1. Okay, now for the part in here, it looks a bit like a triangle, but it's not quite. For that, we have y going from root x to 2, put root x here, 2 here, and we have x going from 1 to 4. Okay, now why would you want it to change the order of integration? Well, it might be easier to do an integral one way than it is the other way. And so that's why you might want to change the order of integration. Okay, so let's do this integral now. So for the first one, integrating this with respect to y, we have 1/3 x y cubed, and then that's y equals 1, y equals 2. Okay, similar for this, except our bounds are different. So plus the integral from 1 to 4. Now having integrated this partially with respect to y, we have 1/3 x y cubed, and this time the bounds are y equals root x to y equals 2. Okay, so let's simplify these by subbing in those numbers. So 1/3 x y cubed, so putting in 2, that's 8. So we'll just change that into 8 over 3 x, and then we subtract. Now we're subbing in y as 1, so we just have minus 1/3 x. Okay, now for this second integral, subbing in 2, 1/3 x, 2 cubed is 8, so we'll change that 1 into an 8. Subtract. Now we're replacing the y with the square root of x, so we have 1/3 x root x cubed is x root x, so we'll change this into x squared and root x, and then dx. Okay, great. So let's complete our integrals now. So they're just integrals with respect to x. So the integral of x is a half x squared. So we have 4 over 3 x squared. We could have combined these incidentally. So minus 1 over 6 x squared. And so that makes this 8 over 6, doesn't it? Okay, so 8 over 6 minus 1 over 6 x squared, 0 to 1. And then over here we have 4 over 3 x squared. Now let's represent this in terms of an exponent. So we have x squared times x to the power of a half. 2 plus a half is 5 over 2. So we're dividing by 5 over 2 plus 1, which is 7 over 2. And then we have x to the power of 7 over 2. Okay, continuing. Okay, so 8 over 6 minus 1 over 6 is 7 over 6. So 7 over 6, subbing in 1 for x. We just have 7 over 6 for this. And then we subtract 0. So, okay, then we're subbing in 4. So 4 times 16 is 64. So 64 over 3. And then this fraction right here is 2 over 21. Okay, the square root of 4 is 2. So 2 to the power of 7. Now we subtract, same function, but sub in 1. So we have 4/3 minus 2 over 21. Okay, so we need to simplify this fraction, or the sum of fractions. So 7 over 6 plus 128 over 6. Now 2 to the power of 7 was 128. So 2 to the power of 8 is 256. Okay, over here, we're subtracting, let's make this over 21. So 7 times 4 is 28. 28 minus 2 is 26. Okay, 7 plus 128 is 135. And we have minus 282 over 21. So we need this to be over 42 because both of these divide into 42. So 6 times 7 is 42 and 2 times 21 is 42. So 7 times 135, 945. And 2 times 282, 564. Okay, and so let's subtract. So we've got 381 over 42. And so we end up with 127 over 14 again. So that matches what we got calculating this in the first way, all right? Except here we changed the order of integration and did it by breaking that up. Okay, question 11. So we've got a double integral. Y goes from 0 to 4. X goes from 1 to the square root of y. And we're integrating x minus y, dx, dy. Now, I've plotted this region for you together with the plane z equals 0 to show you that it's going to come out negative here. And that just means that this region is below the xy plane. And hence, we're getting a negative volume. All right, so let's go ahead and calculate this. Integrating this with respect to x partially, we have a half x squared minus x y, x from 1 to the square root of y. Subbing in, replacing x with the square root of y, we have 1/2 root y squared is y, and then y root y, which we can express as y to the power of 3 over 2. And then we subtract, subbing in x is 1, so 1/2 minus y. Okay, so simplifying this, like terms here, we have 1/2 y plus another y is 3 over 2y minus y to the power of 3 over 2 minus 1/2. 3 over 2, sorry, yes. Okay, and so now simplifying by integrating this, we have 3/4 y to the power of 2. Adding 1 to 3 over 2 gives 5 over 2. 2/5 y to the power of 5 over 2 minus 1/2 y. Okay, so subbing in 4, we have 3 times 4 squared over 4 is 3 times 4 is 12. And here we have a square root of 4 to the power of 5, so 2 to the power of 5. So this is 32 times 2 is 64 over 5. And then 4 over 2 is 2. And then we sub in 0, so we're just subtracting 0. Okay, so this is 10 minus 64 over 5, or 50 minus 64 over 5, which gives us minus 14 over 5. Question 12, double integral as x goes from 0 to 1, and y goes from 0 to the square root of 1 minus x squared. We're integrating y. Let's do this first with respect to y and then with respect to x. Okay, so this is y here. So y is less than or equal to the square root of 1 minus x squared. And so you can see that our region is circular. So y squared is less than or equal to 1 minus x squared. And so this is the interior of the unit circle within some region. Okay, so let's integrate this with respect to y. So we have a half y squared, y equals 0 to y equals square root of 1 minus x squared. So subbing this in, 1/2. Now squaring the square root of 1 minus x squared gives 1 minus x squared. Then we sub in y is 0, so we're just subtracting 0. Okay, and so we're integrating 1/2 minus 1/2 x squared dx. So 1/2 x minus 1 over 2 times 3 is 6, x to the power of 3. So substituting in the 1, we have 1/2 minus 1/6, and then minus 0. So 1/2 minus a 6th is 3/6 minus 1/6, which is 2/6, and so that is 1/3. 13. Double integral as x goes from 4 to 9 and y goes from 0 to x. We're integrating the square root of x minus y, first with respect to y and then with respect to x. Okay, let's consider this region. So D is the set of all points x comma y such that x is greater or equal to 4, less than or equal to 9, and y greater or equal to 0, less than or equal to x. Okay, so now let's sketch this region. Okay, so I've got the axis there. So now let's just sketch the line y equals x. It comes through something like this. Okay, and so next I want to put where 4 is and where 9 is. So let's just make 4 right there and 9, something like that. I need to extend this. Now let's put vertical lines at 4 and 9. Okay, and so in here, this is our region D, which I am shading now. All right, and so we're calculating the volume of a surface above this region and below the surface. The surface is z equals the square root of x minus y. And so if y is less than or equal to x, then inside the square root, we have a positive number. There's a positive out the front of this. So this is above the xy plane. All right. And so we can also describe this surface as x equals y plus z squared. All right. So back to the integral. We expect to get a positive number here. So let's integrate this. So first integrating this with respect to y. Well, we write this x minus y to the power of 1/2, then letting u be equal to, so let's actually do this down here. So let u be equal to x minus y, taking the partial derivative of u with respect to y, we get minus 1. So in a substitution here, we would replace dy with minus du. And so our integral x to the x minus y to the 1/2 dy, we can write this as u to the 1/2 times minus du, but we'll put the minus out the front. So this is what we have here. Okay, so adding 1 to the exponent there, we have u to the 3/2 dividing by the new exponent. This gives us minus 2/3 u to the power of 3/2 plus c. But up here, we've got a definite integral. So we'll put minus 2/3 x minus y to the power of 3/2, y equals 0, y equals x, and then we're going to integrate the result with respect to x. Okay, so subbing in, replacing y with x, we'll get 0 in here. Then subbing in y is 0. We have minus, be careful with the double minus sign here because we are subtracting, minus 2/3, and then we have x to the power of 3/2. Okay, so simplifying this is the integral from 4 to 9 of 2/3 x to the 3/2 dx. Adding 1 to this exponent gives 5/2. We've got to divide by the new exponent. So 2/3 dividing by 5/2 is to multiply by 2/5. Okay, and so we have 4/15, 9 to the power of 5/2 minus 4/15. Let's just put brackets here. So minus 4 to the power of 5/2. Okay, so this is the square root of 9 all to the power of 5. So 3 to the 5th, 4/15, 3 to the power of 5 minus 2 to the power of 5. So 3 to the power of 5 is 343, and 2 to the power of 5 is 32. Okay, 343 minus 32 is 243, isn't it? Okay, so 243 minus 32, not 311, it's 211. So 4 times 211 is 844, and this is over 15. There we go. Question 14, double integral, y goes from 1 to pi on 6, x from pi on 3 to y, sine of x dx dy. Okay, so integrating sine of x with respect to x gives minus cos of x. So x equals pi on 3 to x equals y. Okay, now replacing the x with y here, we have minus cos of y, and then we subtract replacing the x with pi on 3, but there are two minuses there, so that will be a plus cos of pi on 3. Okay, now cos of pi on 3 is a half. Let's simplify this first. And now let's integrate with respect to y. So the integral of cos of y with respect to y is sine of y. So we have minus sine of y plus 1/2 y. And now we sub in replacing y with pi on 6. So minus sine of pi on 6 plus 1/2 times pi on 6 is pi on 12. And then minus sine of 1, so that's plus sine of 1, and minus 1/2. Okay, so sine of pi on 6 is 1/2, so we have minus a half minus another half is minus 1, so pi on 12 minus 1 plus sine of 1. Okay, question 15. X goes from 0 to the square root of 3, y goes to x squared from x squared over 3 to 1, and we are integrating 4 minus x squared dy dx. Okay, so first integrating with respect to y, or y minus x squared y equals x squared over 3, y equals 1. Replacing y with 1 there, 4 minus x squared. Now replacing y with x squared on 3. Okay, so simplifying this, we have 4 minus x squared minus 4 on 3 x squared, and so we can express minus x squared is minus 3 on 3 x squared, so this gives us minus 7 on 3 x squared, and then plus 1/3 x to the power of 4. Okay, so now integrating this with respect to x, we have 4x minus 7 over 9 x cubed plus 1 over 15 x to the power of 5, 0 to the square root of 3. Okay, so simplifying this, we have a common root 3 here, which we can pull out. So 4 minus, now let's place these over 15. So 7 times 5 is 35 over 15. 3 times 3 is 9. 9 over 15. 3. 15 times 4 is 60. So 60 minus 35 plus 9 all over 15. So we have 25 plus 9, which is 34 over 15. And we need to put in the root 3. So 34 root 3 on 15. Question 16. Calculate the net outward flux of the vector field F. Now I'm going to write F as column, x plus 2y, y minus 3x, across the quarter circle. Let's just sketch a quarter circle. X squared plus y squared equals 1, with x and y between 0 and 1. So what we're talking about is this quarter circle here, where x and y are both between 0 and 1. Okay, so what is the net outward flux? So loosely speaking, you can think of this as the quantity of force that goes through this object here. And so you can see I've got it's an animation really of the vector r as the parameter u changes. Okay, so the hint here says parameterize the quarter circle and the normal vector n, and then compute the integral of n, the integral of f dot the normal vector dx. Okay, so this is called a line integral. And so the way we do that is using parameterization. Now this is somewhat premature because in our next tutorial, we'll go through parameterization in detail. So the arrows that you see here, that is F, that's the force field. And then here's our quarter circle shown in black. And then I have a point there shown in red. That is a point on that quarter circle. and another point there in red at the origin. So this arrow here is the arrow from the origin to that point, and so let's call that r of t. It's a vector. So parameterizing the unit circle, we can express a given point p as cos of t sine of t. So any point on this unit circle, there corresponds a t for which that point can be expressed as cos of t times sine of t. And you can see this clearly from letting t be this angle. And so if the distance from the origin O to P is 1, then that's the hypotenuse of this triangle. And so this side over the hypotenuse is the cosine, but that's the x-coordinate of P. And the opposite over the hypotenuse is the sine of t. That's the height here, or the y-coordinate of P. Okay, so this is our point P. And so R is the vector from the origin to P. It's OP, which we can calculate using description of the point. So P minus O written as a vector. And so written as a vector, since we are subtracting 0 and 0, let's write this as a column, cos t sine t. All right, now differentiating this, we have r dash of t. So we're differentiating this with respect to t. So the derivative of cos is minus sine. So we have minus sine of t. And for the derivative of sine, we have cos of t. Here's r dash of t. Now displaying this here, this is perpendicular to r. And so as I change that parameter, you can see what happens. The arrows move. So again, this arrow here is the arrow r, and this arrow here is the arrow r dash, the derivative of that vector r. So as we increase t from 0 to 1, this is what it looks like. Okay, so these are key ingredients in our calculation of flux. Okay, so next we choose a normal vector to that surface or curve, unit normal, so n hat, such that the normal vector dot r dash of t is 0. So in other words, perpendicular to r dash of t. And so coincidentally here, this will be parallel to r itself because we have a unit circle there. So n dash parallel to r. So we put n hat equal to the vector cos t sine t. Okay, so next, flux, the amount of force, roughly speaking, caught by this curve is given as a line integral over c, where c is the curve, f dot n hat ds. And so we can calculate this by putting f of r of t dot n times the norm of r dash dt. In other words, we can substitute replacing ds with the norm of r dash dt. Okay, so calculating all of these things, so up here we can write that the norm of r dash is the square root of the x component plus the y component squared. And so we have the square root of brackets minus sine of t squared plus cos squared t. And so when you expand this square, you just have sine squared plus cos squared, which is 1. So we're taking the square root of 1, which is 1. That norm there is 1. Okay, so now what we do is we replace x with the x component of r. We have the integral over c, but this is t goes from 0 to 1. Now f of r is cos of t plus 2 sine of t, and then we have y minus 3x will be sine of t minus 3 cos of t. Okay, and this we dot with this vector here, dotting that with cos of t sine of t, and then we calculated that the norm of r dash is 1, so this is just dt. Okay, now taking the scalar product, we have cos squared t plus 2 sine of t cos of t plus sine squared t minus 3 sine t cos t dt. Okay, let's get another page. Okay, so the parameter should go up to pi on 2, not 1. So let's change this to pi on 2. All right, so having taken this dot product, let's simplify this now. So we have the flux equal to, now cos squared plus sine squared is 1, and 2 minus 3 is minus 1. So minus sine of t cos of t. Okay, so now let's let u be equal to cos of t. And so then differentiating u with respect to t, we have du on dt is minus sine of t. So this tells us then that we can replace dt with du over minus sine of t in a substitution. Now, what happens to the u for the boundary values? Okay, so u as a function of 0 is cos of 0, which is 1. U as a function of pi on 2 is cos of pi on 2, which is 0. So now this flux integral becomes, breaking this up, we have the integral from 0 to pi on 2 of 1 dt, and then plus the integral, replacing the cos t with u, we have minus sine t times u, and then replacing dt with du over minus sine t. Now, the bounds change from 0 to pi on 2 to 1 up to 0. Okay, so simplifying this, integrating the 1 with respect to t, we have t 0 pi on 2, and then over here we can cancel the sign, the minus sign of t, and so we have integral from 1 to 0. Now obviously 1 is greater than 0, so we can swap this around, but we'll just wait a moment. Integral of, there we go. Okay, and so now this is pi on 2 minus 0, and then we subtract, swapping this around, 0 to 1 u du. So integrating the u, we have 1/2 u squared, 0 to 1, and so we get pi on 2 minus 1/2 and then plus 0. Okay, so we can write this all over 2 as pi minus 1 all over 2. And this is our flux. Okay, question 17. Find the flux of the vector field F. I'm going to write it as a column. So Z, Y, X. And you can see this shown here in my diagram above. The arrowheads are a little bit big, but I think you can get the idea that this is a force field passing through three-dimensional space. Over the unit sphere, x squared plus y squared plus z squared equals 1. And so that ball is also shown there in orange. So we're calculating how much force passes through that ball, or the net outward flux. Okay, so this is given by double integral over the surface S. Now that's a closed surface. F dot n ds, where S is normal to the surface. And so we can trade this in for a triple integral. So this is the divergence theorem, where inside we have div of F dv. Okay, so now we need to calculate div of this force field F. So div of F is the sum of the partial derivatives, each of the components. Okay, so here's div. Now let's calculate this. The derivative of z with respect to x partially is 0. The derivative of y with respect to y is 1. And the derivative of x with respect to z is 0. So we have div f equals 1. So this formula up here gives us that the flux is the triple integral over v of 1 dv. Okay, and so that's the volume inside that ball. So let's calculate this. We know it's going to be 4/3 pi r cubed, where the radius here is 1. But let's calculate this. And so we can write this as the integral, or the triple integral, where theta goes from 0 to 2 pi, phi goes from 0 to pi, and the radius r goes from 0 to 1. So we have 1 times r squared sine phi dr d phi d theta, changing to polar coordinates. Okay, so let's calculate this now. So integrating with respect to r, we have 1/3 r cubed sine of phi, r equals 0, r equals 1, and then that's d phi d theta. Okay, subbing in r is 1, we have 1/3 sine of phi. Subbing in r is 0, we just subtract 0. Next, we need to integrate with respect to phi, and then with respect to theta. Okay, so then integrating sine phi with respect to phi, we get minus cos, so minus 1/3 cos of phi. Phi equals 0 to phi equals pi, and d theta. So subbing in phi is pi, and subbing in phi is 0. Minus 1/3 cos of pi. Minus minus is plus, so plus 1/3 cos of 0. d theta. So cos of pi is -1. So we have minus a third, which is plus a third. So 1/3. Cos of 0 is 1/3. So 1/3 plus 1/3 is 2/3. So the integral with respect to theta of 2/3 between 0 and 2 pi. So this is 2/3 theta from 0 to 2 pi. And so we have 2 times 2 pi over 3, which is 4 pi on 3 minus 0. So 4 pi on 3.